So we're excited to have Dub, who's a professor at George Mason University, talk to us about scaling a PC to thousands or millions of parties. Slides are working.
Okay, forgot to unmute. Thanks for having me. Nice to be here, so to speak. So yeah, I'm at George Mason University. I'm an assistant professor there. I've been there about 5 years. I'm going to talk about two recent works of mine on scaling MPC. So the first one appeared last year at CCS, and it's called Stormy. We looked at computing statistics in Tor, the anonymous routing network. And the second one is a work that's in submission, which isn't exactly a follow-on work, but it's influenced by the first one, so they tie nicely together. So let me start with the first one. So why Tor? A little bit of motivation. Well, the first goal was really actually to try to benefit Tor. My co-authors are very invested in Tor and wanted to see something that would be useful there. This isn't exactly my goal, full disclosure. I was really more interested in seeing what we could generalize about large-scale MPC, but using Tor as sort of the start-off point gave us a good way to sort of nail down parameters and think through what are the right ways to look at large-scale MPC. So in particular, there's so many parameters you can fix in MPC. It's hard to just sort of throw a dart and choose which ones to use and assume. So looking at Tor, which has about 6,000 volunteer routers as the application, gave us kind of a way of nailing these things down without having to make arbitrary decisions. Okay, so I'll talk a little bit about each of these, but so in a paper, we really looked at very concrete parameters, very like specific concerns for the Tor network. In fact, we wrote it in a way that was aiming to hope for adoption. I don't know whether that will really happen or not. But like I said, my interest more was thinking about these broader problems. So the talk will be a little bit different from the paper. I'll give you some insights that we gained that we didn't really bother to publish. So I'll talk about the first two bullets on the next slide, but let me just say that what are the things we want to compute here and why general purpose MPC. So recently there have been a lot of publications on doing simple statistics for Tor using tailored constructions of various kinds, mostly aggregate statistics. And Aaron Johnson, who's my co-author, who knows a lot about Tor, felt there really was a need for some computations that were nonlinear. So median and set union cardinality were the two we focused on here, but he really believes there are many more that would be useful to Tor if we had a general purpose platform for it. So those are the two we did. For both of them, it seemed to make sense to use Boolean circuits, so we focused on Boolean circuits, which is this last bullet here. So the application determining our computational model, we ruled out anything that was for arithmetic circuits at the beginning. But the first two bullets are much more interesting. So what sort of security requirements do we have here? And also what kind of network and performance assumptions can we make about our network for this particular application? So Tor makes a very strange security assumption. I mean, it's not strange, but it's strange for the MPC world. The majority of bandwidth is held by honest parties. Not necessarily the majority of parties are honest. And the reason for this is Tor users want to distribute the load across the network, and there's a very wide range of available bandwidths among the volunteers. So they choose their routers for routing proportionate to their bandwidth. The probability is proportionate to the bandwidth. We could have made an extra assumption also that a majority of the routers were honest, but we didn't want to add any assumptions on top of the ones that are already there. So that's what we worked with in our paper. And then it was important to have some kind of resilience against DOS attacks. We don't want one of these arbitrary 7,000 users, whatever it is, to come and sabotage the computation, because we're going to use a fairly heavy proportion of the bandwidth in the Tor network, and obviously there's other uses for that bandwidth. So we don't want to waste our time computing something and then finding out we can't get the answer. So we looked for a long time at guaranteed output delivery and decided it wasn't quite practical enough. Since then, there have been some advances. I can't say whether it would now be practical enough, but we came up with I think is an interesting sort of intermediate ground that I'll explain later, that gives us basically what we want without full guaranteed output delivery. We didn't formalize this in the paper, but it wouldn't be hard to formalize it. So that's probably the most interesting things that came out of fixing our model, or our application rather. And then in terms of network and performance assumptions, the one nice thing about Tor is that we actually have access to a bandwidth distribution. So that's reported by these routers, and we can get a sense then of what types of bandwidth distribution should we be considering in these large-scale computations. I mean, I don't know whether this is representative or not, but at least it's not uniform, which is a little bit more realistic. And then requirements that imposes on us, we not only want to handle DOS attacks and malicious failures, but also honest failures. So we need to have some way of recovering when honest parties drop out, because we know that's going to happen with these volunteers. So when I hear honest majority MPC with very many parties, the first thing I think of is to elect a committee. And that is obviously, you know, the natural thing to do in any sort of large scale computation like this. So you have sort of two options if you have an honest majority. One is to maintain the honest majority in your committee, which requires a committee size of at least log n. The other is to have a malicious majority committee where you have requirement of only one honest participant, in which case your committee size is independent of n and can be, say, 40 or whatever it is you want to take for your statistical security parameter, a little bit larger if you have multiple committees, which I'll get to. But of course, here we don't have an honest majority. We only have a majority of bandwidth held by honest parties. So in fact, we could have n-1 corruptions, right? If that's the only assumption we're going to make, it could be that one party holds half the bandwidth in the network. So an honest majority of bandwidth, because it could be an honest party holds half the bandwidth, but still the rest of the parties might be malicious. And then of course you can't elect a committee. The smallest committee with an honest party would be size n. So the solution here is actually also the problem. The reason we assumed this in the first place, that we had an honest majority of bandwidth, is because users want to select their routers with probabilities proportionate to their bandwidth. So we'll just do the same. If we select our routers for our committees with probabilities proportionate to their bandwidth, then again, we can elect committees that are likely to have an honest majority of participants. Okay, so that's a fairly easy solution. But a bigger problem arises here, which is that this committee is very likely to have very low bandwidth. And that's because, I think it's a plurality, but anyway, a large number of parties in the Tor router community have very low bandwidth, like 100 kilobytes per second or something like that. So with high probability, we'll end up with one of those guys on our committee. And actually, even if we don't, even in the case where we have uniform distribution over the bandwidth, the truth is you don't want to bottleneck yourself with one single online committee. Your bottleneck complexity, which is the worst case communication in your network, is then pretty bad, right? The way another way of looking at that, the other side of the same coin, which I like to think of in this context, is that we have all these volunteers who are willing to give up their bandwidth for Tor, so presumably they'd be willing to give it up to also compute analytics that'll help make Tor better, but most of them are going to be leaving that bandwidth on the table, right? They've offered us their bandwidth. We elect a small committee and ask them to do all of the work, and now all this other bandwidth is just sitting there unused. We could be using it for this computation. So, you know, we want to figure out how to do that. So the basic idea then is to use many parallel committees, and then with the same restriction that we don't have an honest majority of parties, but an honest majority of bandwidth, we sybil each party down to a basic unit. Okay, so we'll define a basic unit of bandwidth to be the bandwidth of the smallest party in the network, and each party will then hold B tokens. I'll run through this in the next few slides. And then a party with B units of bandwidth might serve on about B committees. It might be more, it might be less, depends exactly on your sampling procedure. And now each of these committees is going to operate by definition at the very slowest possible speed. So they're all going to run at, say, 100 kilobits per second, but you'll have thousands of these committees in parallel, which allows you to get hopefully good bandwidth utilization. So here's a nice little graphic I spent way too many hours on. I've got a bunch of different computers here, and the little people are their units of bandwidth. So the larger computer has the most bandwidth. And after sibling down, we're going to elect based on these units. So we sample at random from the pool, and anyone sampled serves on a committee. Now, of course, bandwidth isn't actually discrete. I don't expect that they will actually throttle themselves or anything like that. They're just, once they're assigned to a committee, they'll just run multiple executions in parallel. So now the first guy is on 2 committees, they'll just run 2 executions, and the bandwidth will lay wherever it lays. I don't actually care that it's, you know, calculated. So we continue doing this. At some point, you might elect someone twice to the same committee, so you have a decision to make here. I'll come back to why we do what we do, but we just throw that one away. So we'll waste a little bit of bandwidth here. And then we can go until essentially we've run out, we can't form another committee, at which point we're done. Okay, so what's the right way exactly to do this? I showed it on the last slide as sampling without replacement. It's actually tempting to sample with replacement. That's what we did in the paper. And the reason is because it makes the analysis extremely easy. So we have an honest majority of bandwidth to start with. If we sample with replacement, then we always have an honest majority of bandwidth that we're selecting from. So I can just say that with probably greater than half, each time I select a new member, I've selected someone honest. So it's a simple analysis, and I'm basically done. I'll need a union bound over the number of committees, but each one can be roughly a size kappa. So this is really nice. The problem is that after a while, you overcommit somebody, right? So each person has B bandwidth units. As soon as I assign someone to B+1 committees, they're going to slow down all the committees they're serving on. So they're not actually contributing the B bandwidth to each, or the unit of bandwidth to each committee that they've promised. And that's fine, again, because it's not actually a discrete utility, but it means then that you stop gaining at some point when you start adding new committees. So you'll fluctuate, right? You might add a committee that actually helps, and then you'll add a committee that hurts, and you go back and forth. So empirically, using the Tor distribution, the bandwidth distribution that's advertised, we see that we get about 60 to 70% bandwidth utilization. We stopped there for this paper because on average, these routers only have about 50% available. So they're spending about 50% of their bandwidth on actual routing. And we felt we don't want to push it up till their maximum, or this really would never fly. So we only used about 25%. So this was really good enough. But for me, it opened the interesting question of whether we could do better. And the obvious thing is to do what I did in the previous slides. You select without replacement. And then you have a guarantee that you won't commit anybody to too many committees. As soon as they run out of units, they just won't be assigned anymore. So the security proof becomes a little more challenging because you may now occasionally have fewer than half of your remaining bandwidth is honest. So our first attempt at a security proof, we looked at a turnoff bound, just claiming that you stay near 1/2 of honest bandwidth at all times. And this works, you can prove it this way, but there's too much slack in the beginning and the end of the proof where there's more variance. And even really pushing the parameters, looking at concrete numbers, analyzing the combinatorics in Wolfram, we still wouldn't really get much above the 60 to 70% that we saw in the first approach. So it wasn't until after publication we actually realized that all you have to do is change your security analysis and you can get nearly 100% utilization. So rather than treating this as a game where I'm sampling and hoping to stay near the mean, just think about permuting all of the bandwidth units up front at once, and then analyze any one of those committees and forget the rest. So the analysis of that one committee is pretty straightforward. And then you can just take a union bound over all committees, and you get nearly 100% utilization. So it ends up being a much cleaner proof. You don't have to worry about any tail bounds, and then the same procedure gives you actually almost full utilization. All right, so some units still go missing because you have duplicates put on the same committee, or because you just don't have enough to form the last committee. We never actually ran through this experiment, but conceptually it seems like it should get very close to 100. Okay, so one thing I haven't talked about yet, though, is what do we do with these committees? If your computation is naturally parallelizable, then that's great. You can just divide your circuit up among those different committees and compute. The much more obvious thing to do here, though, is actually just to generate triples. So remember that our committees are all malicious majority now. So anyway, we're going to be using a malicious majority protocol. So probably everybody here knows what that looks like, but you want to use these authenticated triples. A, B, and C are secret shared with that online committee, satisfying this relationship that C equals A times B, and actually we want them authenticated as well. So we had several thousand offline committees. That's because the offline committee is much more expensive. So generating these triples is the expensive part of malicious majority MPC, and then just a few online committees. And I'll come back to what those numbers were precisely, and whether, why we chose the numbers we did, but the intuition is probably clear. And just a little side note, which will tie in with the second half of the talk. In fact, implicitly, Tor users are assuming a much more than an honest majority of bandwidth. So you actually could have used honest majority committees without having to greatly increase committee size. We could have had kappa size committees larger than malicious majority, but still just dependent on the security parameter. We didn't do that here just because we had to make a decision and go with it, but yeah, so I'll come back to this question, what we could do in the second half. Okay, so let me talk about our other security constraints, which in some sense are maybe the more interesting contribution. So we want to be able to handle honest failure, well, malicious and honest failures. Let's talk first about honest failures. So if a triple generating committee aborts for whatever reason, we just lose their triples, which is nice. So we can just throw that committee away. And in fact, we can even replace it with a new committee. So remembering that what we actually did in our paper, we didn't have full bandwidth utilization. We only used about 25%. We only had 1,000 committees, and we could have pushed it, I don't know, to 4 times that. So what we do is we hold a few in reserve. So we build into our union bound a couple of extra committees, and then if anything fails in the middle of the computation, we can just go and grab the next live committee and have those parties start computing again. Same for the online committee. We have fewer of them and a smaller probability of failure, but we can do the same, hold a few in reserve, and the same impact on the union bound. Okay, so what about malicious failures, which is much more interesting? So large coalitions can prevent our protocol from completing. You can see that, right? If you have a malicious party on each of these 1,000 offline committees, they could have each of them fail, and then you're stuck. You can't go any further. And we don't try to prevent that. Like I said, it looked like that would be too expensive. But we also don't really feel that we need to prevent that. It seems pretty unlikely that a large monolithic adversary that controls, you know, nearly a majority of the parties in Tor is going to use it just to perform a denial of service attack, right? They've got better uses of their adversary at that point. So what we really want is to prevent small coalitions, or really even just a single user, but small coalitions will be fine as well. We don't want some rogue person who just feels like, you know, tearing things down to come in and abort the computation right before the output is reconstructed, because we're wasting 25% of our network's bandwidth on this, and that would be, you know, too easy to do and sort of devastating. So like I said, we didn't really formalize this, but what you would do if you wanted to formalize it is just say that you have a separate corruption threshold for failures. So you have guarantee of output if the corruption threshold is lower. So same as with the honest case, although there's a little star here I'm going to come back to. It's not exactly true that you can just treat it as an honest failure, but basically you can just elect a new committee if one of the committees fails. Right? So that's not so interesting or difficult. The more interesting thing is the input sharing protocol. So if a party gives you bad input, meaning it's not properly authenticated for the online phase, then you won't detect this naively if you don't do anything to handle that. You won't detect it until just before the output is reconstructed. And then at that point, it's too late to exclude that party, and your whole computation is wasted. So what we need is some method for testing an input at the time that it's shared to make sure that it's actually correctly authenticated. If it's not, we want to reject that input, but still continue. So that party shouldn't be able to tear down the computation. On the other hand, if it is properly authenticated, we don't want a malicious party in the online committee to be able to either force the exclusion of some input, right? So they shouldn't be able to target a user and pretend that that user was malicious and exclude their input. And also they shouldn't be able to force the recovery of that input. So we have to balance these two constraints. And we designed a new input sharing protocol that allows exactly that. So I'll run through it fairly quickly. So we define this accountable message functionality, which is basically like weak verifiable secret sharing, slight differences. Differences aren't important enough to describe here. But so you have a sender and a receiver and a committee C. The committee is the online committee that's going to perform the online computation that's trying to get the input from the sender. So the sender is going to send shares to each of the members of the committee. Each member will play receiver in this accountable message protocol. Okay, so the requirements are that when they send a message, first of all, it's private, only the receiver gets the message. And if it's not valid, and by valid, I don't mean authenticated with respect to the online phase, but valid with respect to this functionality. So in particular, if it's not valid for the reveal phase, at the time that it's sent, this party can be excluded. So roughly what you can think of is we have an encryption of a signed message. So you want to be able to prove that what's under the encryption is in fact validly signed without revealing the message. And that happens at sending time. If you can't prove that, then you can exclude. You have to be able to prove that the sender didn't send such a message, it wasn't valid, and then you can exclude that user. If you sent a valid message, it may or may not be correctly authenticated. We'll get to that later. And then in the reveal phase, you can reveal the message that was sent to you and prove its correctness. So you basically just show the message in the signature. Okay, so how do we use this? So we're gonna have two types of secret sharing here. So X is additively shared if it's in these single brackets, and S is authenticated sharing if it's in the double brackets. That means it's authenticated under that same value alpha we use for our triples. And so the input party on input X is gonna send a random mask that's authenticated under alpha. That's its own little subroutine, but it's pretty standard for online MPC. And then also a masking of the input, which is not authenticated. And it does, the send operation here is with using that accountable message functionality. So anybody who receives an invalid message in this step, meaning that they won't be able to prove correctness of the message later, they will just prove that to the rest of the committee, and they can exclude the input party right away. If everyone has a valid message, then they try to verify whether S is correctly authenticated. So if it's not, then they have to find out who to blame. It might be PN, and it might be one of the committee members. So now they use the reveal functionality, the reveal subroutine of the functionality. They'll reveal the shares of S, and now S, because it was random, doesn't reveal anything about the input. So if they all manage to reveal proper shares of S, then the fault must lie on the committee. And if they don't, it means that PN must have cheated and sent a bad S in the first place, and now we know what to do. So we either exclude PN or we just terminate if a committee member is malicious. So a malicious member of C can in fact terminate the whole computation. It's worth noting. But you know, this is gonna be 25 parties out of 7,000, which is reasonable, we think, for preventing denial of service. And then if everything is fine until here, then we're done. So now we can just take this X minus S and reveal it securely. So we prove that that is in fact the right X minus S by using the reveal subroutine. And from there we can compute the authenticated sharing of X and continue. Okay, so that's the input sharing protocol. I did say before that if parties fail in committees, then it's not a big deal. We can treat it as honest. So there is a slight detail here that has to be worried about. When you transfer your triples from an offline to an online committee, there is a selective failure attack that reveals a few bits of the authenticating key. So you know, if we were willing to abort, that would be fine. We would just let that happen and not care, but we don't want to abort. We want to keep going without that committee and use the triples from the other committees. And now you have the possibility that you might leak many bits of alpha across multiple selective failure attacks. So the solution to this is already known. It appears in WRK. But basically, they each use their own alpha in the offline phases. Each committee has its own, and then they use a transfer protocol that transfers it to the online committee's alpha at the end. So just a detail, but worth pointing out. Okay, so I'll give you one slide on how we did. So we ended up choosing 1,000 offline committees and 8 online committees. As I mentioned before, it gives us about 25% bandwidth utilization. We simulate churn using the Tor consensus log. So Tor keeps track of how many routers are available. I think they do this every hour. And so we just looked at the history of their logs to see how frequently parties come and go, and then simulated that in our actual computation. And what we found is that we never needed more than 3 online committees, but usually just 1, which is what you might expect. Over a 24-hour period, 700 of the offline committees disappear. That doesn't, you know, that in a single computation, it'd be much less than that. Say, I don't know, 2% of that. So you'll see, well, here, you can see here, so we targeted 25% of bandwidth, but because parties do go offline and we lose some of those triple committees, it ends up being reduced to about 21%. So that was the impact of the churn. So we're doing many computations in a 24-hour period, not just one, obviously. So we were able to do 36 median computations in a 24-hour period and 150 set union cardinalities in a 24-hour period. And again, you know, we were, like I said, we were focusing on trying to persuade the Tor community that this is something they could adopt. So we weren't really trying to push the number of computations as far as we could. I think there were lots of things we could have done to improve on it. In particular, we weren't looking for 100% bandwidth utilization, which is what most MPC research would do, right? So, so I think these numbers should be taken, well, not that they should be taken with a grain of salt. I think actually they're probably more realistic than we would usually present. in an MPC paper, but you know, but probably there's room for improvement in various ways. I don't know if we're doing questions in the middle. I can keep going if we're not, but.
I don't think there's any questions in the Q&A right now.
Okay. All right, so let me switch over to this new work that's currently in submission, or currently rejected, I should say. So I'll start with another slide of motivation. So an adversary that's corrupting epsilon fraction of the Tor network can target a user and de-anonymize their communication with probability epsilon squared. So just taking what I at some point calculated were my risks of dying of COVID. So if you're afraid of your government and think there's a chance that if they de-anonymize you, they might kill you, then you might want to assume that less than 5% of the Tor network is actually malicious. That's a pretty far distance from what we usually like to assume in MPC research, and it sort of motivated me to revisit, not that people haven't looked at the setting, but to see what we can do practically in the setting where you have a strong, honest majority of parties. Okay, so generally we'll look at any epsilon that's strictly less than 0.5. So we're bounding away from n/2 by a constant fraction. Okay, so we have the following theorem then. So we construct a new protocol. It's secure against active adversaries, static corruptions, and the really interesting thing is that the per party communication complexity in the worst case, so bottleneck complexity again is the worst case bits per party, is sublinear. So each party does better as more parties join the computation. Okay, so that's why I say that this could scale to millions of parties. We got some pushback on that in our reviews, but I'll still make the argument that it's true. And of course, we're not the only people to have done this. There isn't anything interesting you can do that Yuval hasn't done at least 3 times. But we have the following claims, one of them with a little bit of an asterisk we'll have to get to at the end. But this is by no way exhaustive. It's just the best representative in each of these categories currently. But the best prior published work, we managed to remove a log C factor. So you can, if you know the literature, we're going to remove the need to compute unpacked values, which introduces a log C overhead if you want to compute general circuits. Compared to the best Folklore solution, which I think is in itself pretty interesting, and will look a lot like what I was talking about in the first half of the talk, we shave a kappa factor, which, you know, is probably a lot larger than log C. And then the best implemented solution, which isn't always the best measure of what's practical, but a lot of the time Yuval's work should be implemented sooner than it is, but still I think is interesting. The best implemented solution right now is not sublinear. So we do have an implementation of ours, and I can talk about the concrete performance. So let me start with the Folklore solution because it gives good intuition. So it's exactly what we talked about before. You're going to elect a committee of size O of kappa, and then you just run whatever you'd like, right? So let's think now. I'm not interested so much anymore in concrete specifics. I mean, later we can talk about concrete values. Sorry, I got to get my video screen out of the way. So let's just talk asymptotics for the moment. So I'm not going to think for now about generating triples for some online committee and transferring and things like that. Let's just imagine that we, well, okay, I'm getting ahead of myself. So if you have an honest majority committee running in a running whatever protocol you'd like, so most honest majority protocols, if you have exactly n/2 corruptions, I'm not now assuming any gap in the security assumption, so not n/3 but n/2 corruptions, for example. So then there's a constant communication overhead per party. So the cost here would be kappa times C, but the average cost would be kappa times C over n, which is sublinear. So this looks like it's already as good as what I'm claiming for our own solution. And if you use malicious majority committees, then the per party communication cost is kappa times C, and there's kappa parties on the committee, so it ends up being kappa squared C to do this evaluation. But then again, you get to divide by the total number of parties in the network. But of course, this is cheating, right? And this is the point here, is that really when you're thinking about a strict honest majority, or even anytime, it doesn't have to be an honest majority, but if you're bound to below n-1 corruption, so even if you had 3/4 of the network were malicious, and you probably want to form committees. And when you're forming committees, it doesn't make sense to talk about communication complexity, you should be talking about bottleneck complexity. So the per party, or the average communication complexity here, is really a complete cheat. This is not, in fact, sublinear communication if you look at the worst case, right? The worst case parties here have to send kappa times c and kappa squared times c. So it's a pitch for looking at bottleneck complexity rather than the standard notion of average of communication complexity. So the bottleneck complexity here is not sublinear. So there's an obvious solution here, which also looks a lot like what we talked about in the first half of the talk. We're just going to have many parallel committees. And now, because I'm only interested in the asymptotics, it's easier just to imagine that they just chunk up their circuit. Okay, so we'll divide the circuit into n over kappa chunks, or rather kappa over n chunks, one for each committee. And then what you get here is, well, you end up still with worse bottleneck complexity than you did average case complexity, but you do now get the sublinear claim. Okay, so that's nice. You lose a factor of kappa here because when you go to transfer shares of wires from one chunk to another chunk, you might be tempted to say party one sends his share to party one on the other committee, and of course you can't do that. If you have half of one committee is malicious and half of the other is malicious, there's a good chance you're going to reveal too many shares between the two. So you have to reshare each of your shares to the next committee, which introduces a kappa overhead. Okay, so you end up with kappa squared bottleneck complexity here. You don't have to pay that penalty in the malicious majority case, and that's because you can use a PRG to transmit these shares. So you do still have to reshare your share as you communicate from one committee to the next, but if you share seeds ahead of time, then you can use pseudorandom shares and save that communication. So you save a factor of kappa there. I'm treating all kappas as the same here, but of course in the honest majority case, kappa is much larger. It's something like 250. Well, it's not kappa that's 250. It's the same security parameter, but the committee size as a function of kappa is actually, I think, closer to 400. And the committee size as a function of kappa in the malicious majority case is like 25. I'll come back to that when we get into concrete costs. Okay, so here's where we're hoping to save at least a factor of kappa, which is what we do. But now let me talk a little bit about the other approach, which is to compute on packed values. So I'm going to give a one-slide overview of Damgard Nielsen. Damgard Nielsen is used in a lot of the recent literature. It's been very successful approach to large-scale MPC. So everything in this slide, I'm going to use Shamir secret sharings. This is a degree D Shamir secret sharing. And we're going to have an online and an offline phase. I'll start by describing the online phase. So the parties are going to hold what I call double sharings. These are random values that are shared twice, once as degree D polynomials and once in degree 2D polynomials. And they want to multiply their shares of X and Y to get shares of XY. Okay, so they'll do this locally, each party computing the product of their shares till they have a degree 2D polynomial. They subtract off this mask and send the masked value to the central dealer, who can reconstruct XY minus R and send that value back to everybody. And then they can compute shares, a degree D sharing of XY by subtracting that, adding that constant into their share of R. Okay, so it's a very simple procedure. The dealer here is just doing degree reduction for them on a masked value. So the only thing you need is these double sharings. And the naive thing to do would just be have everybody send a random value around and sum them up, right? And then you would have a guarantee that it was in fact random. That's pretty wasteful. So the real insight in Damgard Nielsen is that you can extract more random double sharings by using an extractor. So they use a Vandermonde matrix multiplication to get H double sharings out of a single OOD communication round. So I'll actually do the accounting for you. So here every party has to send 2 values, but these are secret shares. So it's going to be 2 N values. So 1 share to each party. And the number of encoded values here is H, which is in the N over 2 case is N over 2. Okay, so per gate, the cost here is actually just 4 field elements, which is nice. So we're actually at a constant. And then in the online phase, each party has to send 1 value to the dealer. They receive 1 from the dealer. I don't usually count receiving in communication complexity, but each of them will have to play the dealer 1 over N times. And in that case, they send N values. So it ends up being a single element amortized. Because the total is 6 field elements per gate for Damgard Nielsen. And the very obvious idea here is just to do this on packed values. If you don't know what packed secret sharing is, I'll let you look that up offline. But I mean, basically, you load extra values into your polynomial and you build some slack into the degree. So you can just do this straight away on packed values, and your communication complexity gets much better. So you're not going to get n/2 values, but you get O of n values in each of these encodings. And then because you use this extractor, you also get an extra O of n there as well. And so now you can see that we're starting to get sublinear. Right. Same communication in the online phase. I'll have to talk exactly what that looks like or what you can do with that. But I mean, you're sending one value and you keep them packed so that you still have O of n encodings in each multiplication. All right, so now we have a sublinear communication, which is great. The problem is, what do you do with these packed values? How do you compute on packed values? And this is where we have a log C blow up in the circuit size. So this actually goes back to DIK10, who showed that you can take any circuit, and if you're willing to blow up the size of it, then you can make it so that it's SIMD friendly, so that you can compute on packed values. Basically, you have to permute the wire values in between each of the layers to line them up the way you want. Okay, so we're going to try and shave that log C factor. So what else could you do? You could try to send packed values to some online committee, but then notice that you have to keep your threshold the same, right? Because you can't reduce your degree of the polynomial then if you want to keep the packing. And so now you have a very large committee to ensure that you have the same corruption threshold in your committee. So this is going to end up, you will have sublinear communication here, but you're going to end up with a log n kappa value in the numerator. We're hoping to do better than that. And if you unpack and send to a small online committee, which is what we did in the first half of this talk, then you lose your sublinear claim, right? Because now you have to send a share for every gate in the circuit, and you're not encoding anything more than that one triple, and so you end up with constant communication per gate, which is completely off the table. So what do we do with packed values? So this is basically the main insight of our result. So we're going to construct packed triples. So we're not actually going to use the Damgard-Nielsen double sharings of R anymore. We're going to use them, but we're going to use them to generate triples. Okay, so here, because they're packed, we still have our sublinear claim. So we'll communicate O of n values per party to share A to share B. I'll go through it in a few slides, but you know, everything's packed, so you get even though you have to send a share to every party, or O of n shares to every party, you still have O of n squared encoded values. Then we elect a malicious majority committee, and we send to them additive sharings of the packed sharings. And that's the main insight here. So we're going to keep things packed, but so that we don't have to maintain our threshold, our corruption threshold in the online committee, we're going to additively share the packed sharings. So now we have a double sharing, a nested sharing of these triples. And we still get to claim our sublinear complexity then. So we only have to send a single single field element to the online committee to encode O of n triples. And now the unpacking can just be done locally. It's a local operation because it's a linear operation. They can do it on the additive sharing. So they unpack the packed triples inside of the additive sharing so that they can extract O of n triples without communicating with each other. Okay, so now we've sort of pushed communication to computation. We'll have to come back to that. But we get to maintain our sublinear communication, except now I have to talk about the online phase, right? So in the first half of this talk, we just used those triples then for an online phase, which had O of C communication per party, right? So everybody has to open a triple at each gate. And we're trying to avoid that. If we want to talk about bottleneck complexity as before, we need to somehow distribute that work. And the answer is just like before, we're just going to make multiple unpacking committees and online committees. So same as before, we'll have n over k online committees. And when we send these additive shares of packed values, we'll split them up among the committees. And then as they compute the online phase, they can send chunks of the circuit over to each other. Again, using that PRG trick, because we're in the malicious majority setting with additive shares, they don't have to pay this extra kappa factor, and we shave a kappa factor off of the Folklore solution. Okay, and now we can use standard circuits, so we also save that log C factor over the DIK approach. All right, so let me just quickly run through what the whole construction looks like again, because it was all pretty fast. So in the first step, we are going to use Damgard-Nielsen. So everyone's secret shares everything that doesn't have a 2D is just a degree D sharing, but they're going to secret share these values. And then locally, they will do the matrix multiplication. They do this for A, B, Ri prime, and Ri prime again. I just wrote it for A. And then they use the dealer to compute A times B, so they get shares of A times B. Then they do an additive sharing of these three values and send them to one of the online committees. And the online committee interpolates under the additive sharing to get to extract the triples out of the packing. Okay, and then they perform the online computation. So what does the online phase look like? I'm just going to give you 3 lines because we just lift it right out of Cheetah et al. So we assume that we have triples that are secure up to additive attack. I haven't talked at all yet about malicious behavior, but we'll come back to that. But that's what we assume in our online phase. So triples, additive attacks, it means that the adversary might manipulate things. So the triples may not be good triples, but the manipulation is in some sense blind. All they can do is add a random value, add a value of their choosing to the output. So you have A, B, and AB plus delta. So that suffices for an efficient online phase where you basically just evaluate things twice. Once you evaluate C of X and once you evaluate alpha times C of X and you compare the two. Okay, so that's basically what we would do in the online phase. We didn't even bother implementing it. There is actually an important difference here. We have we actually don't have honest majority in our online phase, so we had to tweak their protocol slightly to make it work for malicious majority, but it wasn't very interesting. Okay, so what about security in the offline phase? That's kind of the more interesting thing. So additive attacks are allowed, which is nice, and that makes things a lot simpler, but there is still a problem here. It's called linear attacks, which is introduced only when you're dealing with packings. Here's the basic attack that we have to handle. So let's suppose I'm trying to compute A times B of degree 2D. So that's a local operation. I'll take my share of A, my share of B, and multiply them together, and now I have a share of AB of degree 2D. But let's consider Lagrange coefficients for interpolating the first element of B and the Lagrange coefficients for interpolating the second element of AB. Okay, so these are both polynomials. We can write down what these Lagrange coefficients are. And now imagine an adversary modifies the shares, the first D plus 1 shares of A by adding this ratio of the Lagrange coefficients. When you multiply together, you can do this algebra offline, but what ends up happening is you introduce the element in the first slot of the B's packing gets added to your output in the second slot of the product. Okay, so you're trying to compute A times B. If you look at the element in the second slot of A times B, I can add to it the element that was in the first slot of B. And this is not this is not what we'd call an additive attack, because an additive attack, it shouldn't be, the value I'm adding shouldn't in any way be dependent on the input values. And so this is something worse than an additive attack, and it can be generalized. So I can add any arbitrary linear combination of the input packed values. So we weren't the first to notice this. Genkin et al. Had to handle this as well. And the solution is fairly simple. So notice the adversary here is modifying the first D plus 1 shares. This is no longer than a degree D polynomial. So all we have to do is check the degree of the resulting polynomial to make sure that it's okay. And one thing that's nice in our construction is that because we're only doing a depth 1 circuit, because we're just basically preparing triples for use later, we only have to deal with this one time. So we can just batch our degree check across all of our triples at once and amortize the cost away. All right, so in contrast, if you were to compute unpacked values, then every time you get to a multiplication gate in your circuit, you have to worry about this linear attack, and you'd have to do some kind of a check to make sure it didn't happen. So we don't have to worry about that. We get a much simpler proof, but also I haven't worked through what the cost is for GIP to handle this, but you know, it seems like it should be better to do it once. So what about computation? So that becomes our new bottleneck, actually, right? This unpacking is fairly expensive. I can do the accounting for you if you'd like. Running a little low on time. You know, the main cost here is FFTs, and because we're doing it on packed values, so you only have to do C over N of them in the triple generation phase before you get to the unpacking committees. Yeah, I'm not going to run through this now because I'm actually blanking on what the math looks like, but you can work through the algebra. It's not too difficult. But anyway, I mean, what we end up with is still a computational cost that reduces with n, which is nice. But when you compare it with, say, the Folklore honest majority solution I came up with before, we do worse than they do. So they have a log kappa term in the numerator, we have a log n term in the numerator. So eventually, if you get far enough out where both are dominated by computation, you could imagine that they'll start to outperform us. But in practice, that doesn't seem to be the case. So we extrapolated, we implemented this for like, I think 16 parties and then extrapolated. Well, the computational costs we actually simulated correctly because you don't need any networking for that, up to 1 million parties. The communication costs, of course, a lot harder to do a convincing experiment with 1 million parties, but we just extrapolated. We included all of the network overhead for, that was introduced with 16 parties and then extrapolated the cost. And we do somewhere between 20 and 35 times better than the Folklore solution in that range of 16 to 1 million parties. And that's on a 10 megabit per second line. So we ran our experiments on 1 megabit, 10, 100, and a gigabit. One thing to note here is that we get to run on committees of size about 25. So even though I've been saying O of kappa, the honest majority, when you start with n over 3, your honest majority committees end up being quite a bit larger. Actually, 430 doesn't sound right to me. That might be a mistake. But anyway, it's at least a factor of 10 improvement in the committee size. So even though we have this extra cost in computation, we still do quite a bit better than the Folklore solution. We haven't compared to GIK yet, and we should do that. And that would be interesting to see. So one application, though, that I think is especially compelling and is a place where we actually do considerably better than GIK, is triples as a service. So if you could get 1 million parties recruited, which only Google could probably do, or Apple, we can generate 320 million triples per second. So you could have people do this overnight for just a few minutes or less than a few minutes, and then the next day they could hand them off to parties that need to use these triples in their computations. But even if you could only recruit a few thousand parties, 10 minutes is all you need for 1 billion triples. And at that point, the next day, I imagine it would look a lot like what our first half of the talk looked like. So some committee comes to you and says, I want to do a computation. It doesn't matter how many parties, we can handle n-1 corruptions now. And however many parties, they just have to receive their shares of the triples from whatever committee happens to be online, right? So although I need 10,000 parties online for 10 minutes overnight, which isn't that unreasonable to think about, hopefully you could even do this on your cell phones, although the TCP connections might be a challenge there. But anyway, I mean, if you can imagine getting 10,000 parties to run this for 10 minutes at night, you only need then the unpacking committees are the ones that have to send the triples. So you only need 25 parties assigned to the same committee to be available the next day. And there's high probability that well, I mean, it's certain that some of them will be. So you can sell those triples then the next day when parties need them. They'll just go to whatever committee happens to be available. I actually only realized this late last night and didn't think of the right way to present it. But originally we were actually only analyzing this in our construction, and here we save a factor of kappa. So when I said that we have a communication cost of kappa C over n, that kappa disappears if you're not worried about the online phase. So that kappa was introduced when one committee had to send shares to another committee in the online phase. But if you don't have to chunk up your online committee, if you're actually willing to perform your whole computation in a single committee, which is what we did in the first half, and I think in practice makes sense. I don't think just to gain the full claim of end-to-end sublinear communication to chunk up your circuit among multiple online committees probably doesn't make sense, right? And we demonstrated that empirically in the first half of the talk. So in that setting where you're really only counting the communication complexity required for generating triples, we shave a factor of kappa. So nobody protested, but if you actually want to look at end-to-end analysis and compare it to GIK, we shave a factor of log C, but lose a factor of kappa, and arguably, well, those will be similar. I mean, here, our function of kappa ends up being about 25, which is maybe a little bit bigger than log C, but I don't know what the constant overhead is in GIK. So my guess is we would still win, but it would be close. But if you use it, if you view the right way of using this construction as this triples as a service, which is what I think is the right way of doing it, then we actually save kappa log C. Well, log C, and we don't pay the kappa as compared to GIK. So then it would be a clear win over their construction. So just a few odds and ends that I thought were interesting. We don't actually need the dealer in our offline phase, so we could actually just reshare these degree 2D sharings of C, because in the end, all we're using is additive sharings anyway of these values. So we could actually cut out that whole step and save quite a bit of communication. But because computation is our bottleneck, it actually is better to do the degree reduction and have lower degree polynomials to interpolate in our online committees. So simpler and less communication, but not actually more. We also didn't present it, but came up with a more efficient online phase where we hand them authenticated triples rather than just forcing them to use 2 executions. So that saves half the communication in the online phase, but it costs more than 4 in the offline phase. So that's something that could be useful. And then something we want to investigate is something along the lines of what we did in the first half of the talk, where we build some resilience for failures. And here, you don't have committees that you can just throw away in the offline phase. Everybody's in one monolithic committee, so it doesn't seem like there's an immediate way of doing that. But what you could do is you can build some slackness into your packing parameter. Since communication isn't even our bottleneck anymore, you may as well pack a few fewer triples, and then if a few parties go offline, you can still interpolate and you don't need them anymore. So that's something we might experiment with, but we haven't looked into it concretely. And that's all I have. Thanks.
All right, let's thank Dov for a great talk. So there is one question in the Q&A, and you guys should feel free to type more as I'm talking, but this one question reads, can you expand on the double sharing procedure?
You mean Damgard Nielsen?
I think so. It's from SMU.
I have to figure out how to get, oh, okay, yeah, so I just stopped sharing my slides, and now I gotta find my Zoom window. Sorry. Oh, I am still sharing my slides, that's why, okay.
They're just not in full screen.
Sure, right. Yes, I mean, I encourage you to read Damgard Nielsen. It's kind of a seminal work, but the question, I guess, is this part, the offline phase, how you generate these random sharings. And so everybody is going to send a single secret sharing of RI. So, and then, like I said, naively, what you would do is just sum those up. So if I sum my shares of all the RI that I received, then what I get is a double sharing of a random R. The main goal here is just to make sure that it's random. So we can each generate our own RI. Now we'd have to combine them in some clever way to give us a truly random RI. We don't want the malicious party to be able to dictate what the result is. So if you just combine them by adding them, you don't get constant communication per gate. You have to send, each party has to send here n shares of RI, and if you add them together, you just get one value as output. You'd like to get O of n values as output so that you can claim constant communication. And the observation is that you can just, you don't want to just simply sum them up, you want to combine them. You take random linear combinations, well, not random linear combinations, you take clever linear combinations of these values so that you end up with multiple random values, each of which you can claim is truly random. And as long as the dimensions of this matrix are large enough, and you choose the right type of matrix, so in DN they describe the van der Waals matrix, then you can actually claim that each of these values here, R1 to RH, is in fact uniform. Okay, so basically what you're taking is random linear combinations of these RI that were shared here by each of the each party I, and instead of summing them up and getting one value, which you might call R1, you'll take linear combinations of them to get H values, where H is a number of honest parties. And then you have constant communication per party because you get O of n double sharings out of it instead of just one. So if that wasn't enough, you know, explaining a paper in one slide is a challenge. But I'll point you to their paper. It's worth reading.
So since there's nothing else in the Q&A, I want to ask one quick question also.
Sure.
So you mentioned at some point that you were going to use PRGs to transmit shares between committees more efficiently. I was wondering if you could say a little bit about that.
Yeah, so imagine you have two committees that so one committee wants to, so you hold single wire value in one committee. It's an additive sharing of that wire value, and you want to send shares now to a second committee. So like I said, you can't just send party one's share to party one and party two's share to party two, because you may reveal too many values, right? So instead, if you've pre-shared seeds between these two committees, then everyone can just agree, the first n-1 parties can agree that their share of P1's value will just be the pseudo-random value they expand out of their seed, and then P1 just needs to send one corrective share to party one on the other committee. So it's a resharing, but you don't have to send O of kappa values to do the resharing. You can just generate n-1 of the shares pseudo-randomly and then correct it with the final one. Oops.
Yeah, that's really neat. And we also have one more question from Casper. So is this feasible to use for large-scale voting, since online voting is getting more and more requested in these times?
I don't know. I think wisely our community moved away from using voting as the target application for MPC. So I'm not going to endorse that idea. Nigel is shaking his head. So one thing actually I do want to say, because I get bothered by this claim repeatedly, there is some very nice work in our community about, sorry, it's nothing to do with voting. Just popped into my head though. There's some very nice work on committee-based MPC, where the assumption is that we don't want to communicate with O of n parties. And so we need to find some clever way of assigning committees so that each of us only talks to log n or polylog n parties. There are papers out there showing that a single Linux server can handle 40 million TCP connections simultaneously and efficiently. So I don't think that our community should keep embracing this as a practical concern. It leads to some interesting theoretical questions maybe, but, and admittedly, I don't know how you would do this on a cell phone. So maybe, maybe there are still cases where you don't want to talk to O of n parties if you're trying to scale MPC up to a million. But I'm not convinced that this is a really important practical concern that we should be thinking about. I mean, if Android can't do 1 million TCP connections today, it's only because we haven't decided there's need for it, not because it's a real impractical or impossibility. So I think it's a superficial question, and I'm not trying to knock that research. I think it's very interesting, and I don't doubt you could find settings where it's important. So it's not that it's not important research, but I think that, since I'm going to resubmit this work, I may as well say now publicly that I don't buy that that's a real practical concern.
Makes sense.